Welcome back. So during last week lecture, we tackled the problem of solving Gaussian integrals using path integrals. And we saw that that enables us at least to solve a subclass of problems that can be basically reduced to a sequence of very automatized operations. So basically any correlation functions can be reduced to a simple combination of contractions, where each contraction is nothing but a two-point functions. That is the inverse in the operation sense of the operators entering defining the quadratic part of the Hamiltonian. So just to remind the main results of last week, the generating partition function, generating functional can be written as an overall constant, which you can forget. We only put there for sake of dimensionality. And then an exponent that will involve, now I'm going to write explicitly the integrals, two source terms and a two-point correlation function, where the 2.4 correlation functions is actually the solution of the differential equation, distribution-based differential equation. Now, clearly, if this equation here can be solved, like it is the case for many interesting situations, then of course you have a way to compute arbitrary correlation functions. Okay, that's very nice. It's quite useless if all we can do sort of ends here, right? Because, hey, what can you do with Gaussian integrals? It's like being only able to solve the harmonic oscillator. That's important. You understand springs. But if all you could do in physics was to solve springs or pendula under certain conditions, then of course we wouldn't have sent a man to the moon. Okay. So what to do in situations in which the Hamiltonian is not quadratic? And this lecture will be about the case in which you can treat the non-harmonicity of the potential of the Hamiltonian as a small perturbation. So today we're going to define perturbation theory. Now, when talking about perturbation theory, there's a lot of misconceptions that are being spread over both the didactic and teaching literature and the web. And that perturbation theory is basically synonymous of solving weakly coupled theory. Of course, there's a connection between perturbation theory and weak coupling, and my screen is not refreshing, which means that there's some kind of problem, I guess, which I don't understand. Hold on. So possibly the broadcasting was stopped, and let me try to restart the broadcasting. Maybe we are subject to bombing. I hope not. Now the problem is that actually my internet connection on the iPad is gone. So trying to figure out what's going wrong. No, apparently it's still there. Privacy warning. Okay, now it seems to be all back on shape. Don't know what's going on. So I go back to here. I go back on sharing. And you should be seeing my screen now. Okay. Now, why isn't perturbation theory not synonymous or weakly coupled? And I think it's worthwhile to spend a minute discussing this issue. Now, clearly, the way we are introduced to perturbation theory up to the point where you are, at least for physicists, I don't see the mathematician in the bunch. I hope she was not scared away by field theory. But okay. What I was saying, yeah. The way we are introduced essentially is in quantum mechanics. We start with a Hamiltonian. We have an unperturbed Hamiltonian and a perturbation. And then we look at, I don't know, energy levels. And the energy levels are normally written as a series of perturbations and so on and so forth. And the same happens for the wave function and so on and so forth. There's nothing wrong with it, right? But the idea there is that this, the idea behind it is that this potential is perhaps some function of form times a small parameter. And if you make the small parameter small enough, then you can make these energy shifts small enough. And therefore, you can actually compute the corrections to the spectrum to any desired accuracy in the vicinity of the unperturbed Hamiltonian, basically by Taylor expanding the energy around it. And again, nothing wrong with that. However, the fact that you have a small parameter doesn't necessarily imply that you can use perturbation theory. Let me give you a simple example. We exist. We exist because there are atoms. And atoms are electromagnetic interaction, actually probably almost entirely Coulombic interactions between electrons and nucleons and protons and electrons, of course. But let's stick to the simplest atom. The hydrogen atom exists. There is a bound state. A bound state is basically a pole in a correlation function. It's a singularity in the spectral function, right? Now, the fact that there is a bound state, you can never get the singularity by Taylor expanding a function outside the singularity, right? So the fact that we have a bound state can never come from perturbing free plane waves. There's no way you can take a small perturbation of a plane wave and make it an hydrogen atom, right? Because an hydrogen atom is very far from a small perturbation. Yet, we know that electrodynamics, in particular quantum electrodynamics, is a perturbative theory because it's one of the greatest success of theoretical physics, the ability of predicting perturbative effects in QED to an amazing degrees of accuracy. It is actually the most accurately tested physical theory we have had ever. And in order to do that, we use the fact that alpha over 4 pi, the fine structure constant, is in natural units roughly 1 over 137, which is in fact a small expansion parameter. So when you look at scattering, you can actually work and, first consider tree level, then consider radiative corrections, which involve 2 powers of alpha, and organize the contribution to the scattering matrix as a power expansions of alpha, right? I'm running onto a subject that now everybody should know, even though I'm not asking to know this, I'm just telling you. So in scattering problems, we are assuming perturbation theory, but we know that it doesn't necessarily always work. And there's a reason behind it, is that scattering problems rely on the concept of collision, right? And the concept of collision, remember your first year when you were studying URTI, collisions, right? What was one of the main hypotheses you were using in order to define a collision? The impulse approximation, remember? Which basically said that the collisions takes place in almost instantaneous time compared to the rest of the time. Like certainly on the times, if the interaction between, I don't know, if the interaction between some comet and the Earth would take place over time scales that are comparable with a year, obviously, this would not be a collision, would be something like following up the Earth for a long time before moving away, right? I don't know if this is a really good example, probably not, but I'm trying to pin down the fact that for collision theory to make sense, you need to assume that the times while in which colliding objects remain interacting can be considered small compared to or instantaneous, right? So, but if you look at the interacting theory of quantum electrodynamics, I don't want to go through that because, of course, it's another course business. But I like to derive QED in path integrals, but normally this is not the way it is done in introductory course. I am assuming that Albino went through the interaction representation. Albino Perigo, right? An interaction representation, you have time order products, and then in the exponent, you have like integral over times, and there were Hamiltonians and blah, 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 right? Now, in order to perform Taylor expansion, then you're Taylor expanding this. This is the interaction Hamiltonian. Now, in order to be able to do that, you must assume that the time in which the perturbation remains active is not arbitrarily large, right? So if it was arbitrarily large, no matter what coupling constant you put there, the integral will eventually sum up to a large number, right? And you would not be able to expand this in Taylor series. And in fact, if you take a proton, you put an electron nearby, they are going to stick together for a long time, which means if you want, they exchange a large number of photons. And as soon as they exchange order 137 photons, the total contribution is of order 1. Because anytime the effect scales like 1 over 137. So the fact that you can use perturbation theory, strictly relies on assumptions that very often involve physical scales, not just, dimensionless parameters. Now, it can happen that physics is such that you always are in a perturbative regime. This is, as far as I understand, the case for weak interactions. I'm not aware of any detected non-perturbative effect in weak interactions. Maybe there is, it's just my ignorance. But I think it's fair to say that the range of applicability of perturbation theory in weak interactions is larger than is in QED. Okay? Certainly is much, much larger than it is in quantum chromodynamics, theory of strong interaction. But even if you take the weakest possible force, the gravitational force, hey, we got galaxies, solar systems, they're bound systems. It's not a weak perturbation. Solar system and galaxies are non-perturbative effects, even if the forces that holds them together is the weakest possible one. So weakness of the force does not immediately translate into perturbation theory being useful. Okay? You have to be careful. And I have no particular wise algorithm to give you other than be careful. And I want to prevent a problem that I see happening all the time in exams by giving you the answer before I ask you the question in the exam. Because I used to fail, not fail, but to catch, you know, unfold to many students with this question, to the point that I decided that it was unfair towards them to ask this question. And it's a very simple question. Suppose you have a theory you want to compare to experiment. Maybe the y-axis is where the experimental point is. I don't know. And maybe this is a momentum scale, whatever. Here is where you perform the experiment. Here is the experimental point, and maybe this is your theoretical prediction without the perturbation, or to lead in order in the perturbation. Okay? Then you say, okay, let me go to next to lead in order in the perturbation. And you maybe get this. What would you conclude? A, the theory is working. B, the theory is not working. Now, I'm not going to go through asking you directly the questions, because this is precisely the question that gets everyone failed. This is telling me the theory is not working. Who can tell me why? You see, this is the first order perturbation theory, and this is the second order perturbation theory. What do you immediately notice between these 2 points?
That they are very different.
They are very different. So the second perturbative corrections is not a correction at all. Is as large as the first order correction. So anytime the second order perturbation theory is as large as the first one, you should not trust perturbation theory. Well, you may say, I hope that the third will be here. Fine. You know what I mean? But then is an act of faith, is not science. So perturbation theory is a strong tool, but only enables you to do better than what you already have, or to test very, very, very small effect. In fact, the first successful application of perturbation theory was the understanding of the hyperfine structure of the hydrogen atom. But you need to have non-perturbative effects to get the bulk of it. Okay? Is this clear to everyone? So perturbation theory, but sometimes the unperturbed result is so trivial that all your physics basically sits in the first perturbative correction. Like in QED, the unperturbed case is electrons and positrons just pass through each other without even noticing each other. And that's why if you look at the, I don't know, if I have a collider, well, normally electron positron, they are in head-on colliders, right? Well, what's the point of taking an electron sitting and shining a positron on it? But let's assume for a moment that this was not the case, and then maybe we can do electron proton or whatever. Okay. But same if I'm in a lab frame and I have an electron here and a shine a positron, and I have detectors here, and the positron comes this way, where do I get most of the signal in the detector? Right here, right? But what all perturbative QCD is all about is that basically every so often, with some highly decreasing probability, I get signals also around. That's the Rutherford experiment, the famous Rutherford experiment, right? That he shot electrons and imagining to go through, and then he found out that
Many of them were coming back. Of course, most of them were going through. This is what the story doesn't tell. But oh, say it better. I said something wrong. Most of the electrons don't go through on a metal sheet. But why is that? Because a metal is electron nuclei collisions. How many protons there are in a normal metal? Tens, right? And therefore, the coupling is not 137, is Z times 137, right? And this is of order 1 very soon. So that's why when you do Rutherford experiment, you really see the electrons getting back to you. Okay? But that's a non-perturbative effect. It's called a Rutherford cross section because ultimately the experiment is the same, but it's not in the same conditions of Rutherford. Or else you would not be able to do 3-level calculations whatsoever. Am I talking about concepts you have already heard? Okay. Sorry for being, this is all outside the course, but I like to spend some time. I used to spend more when I was in life to connect to your courses in physics, to see same things from a different perspective. Okay, so now let's go back on our core business. And I want to introduce perturbation theory in the way that is probably very different from the one that you've heard from Albino. Not because I think it is wrong, absolutely. I'm sure he has done a perfect job. But on the other hand, because I want to be practical rather than comprehensive, because I want the idea to convey to you very practically, and then once you have the idea, you can use it everywhere. So let's say we have a field theory. And this field theory is defined by Hamiltonian, which contains my standard quadratic Hamiltonian, which will be the usual for sake of definiteness. Okay. And on top of that, we're going to put the usual 5 to the 4th term. Well, why can't I put the 5 to the 3rd? Who's going to tell me? Why can't I put the 5 to the 3rd? Let me say the. Huh?
Maybe
I didn't hear.
Maybe for symmetry reason.
Let me focus the question better. Why can't I put the 5 to the 3rd alone? But if I put 5 to the 3rd, I must put 5 to the 4th. You see, there are many things in field theory you don't think about if you don't think physically. You only think in terms of mathematics. So what would happen if you would have a 5 to the 3rd here? Let's think about this for a moment. Phi is a real number, positive and negative.
Unbounded theory.
Exactly. What would the system prevent? What would prevent the system to getting on the spin negative and participating towards the most negative energy? This would not be bounded from below. And since my integrals phi goes from minus infinity to plus infinity, this is not a well-defined theory. Of course, I can do that as long as I have a higher power that eventually saves the day. And that must be an even power. So the largest power in the field theory must always be even for your mathematics to be represented in a physical theory. And you might say, well, hold on, QED. I do this. This is cubic, right? 1, 2, 3. And I would say, no, this is quadratic in phi and quadratic in mu, because f mu nu is quadratic in mu, and there's a linear coupling between them. Okay? So QED, of course, is well defined. QCD, on the other hand, you will discover, is tricky because QCD will contain FFF, but fortunately also contains FFFF from non-abelian couplings, gluon, 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 gluon interactions. And therefore it's safe. Okay? Going back to us. So, okay, so the idea is to be practical. Let's compute a 2-point correlation function in this theory. And I've put a 4 factorial here for reasons that perhaps you have guessed, but will become clear in a moment. But essentially, is the number of weak contraction. Eventually, what we have to do will be factorial in the polynomial of the field. So, you know, once again, even if my coupling is small, but I have a factorially large terms to sum, the sum of many factorially small but factorially large sum could be of order 1. Right? So the fact to rescale the coupling here is to make sure that, you know, once you match your experiments to the term lambda and you decide that you are in the perturbative regime, you're safe to do that. Okay? Because your effect would be of order lambda for the correlation function, not for the single contribution to the correlation function. Let me go to the stepwise. So let's say we want to evaluate the following 2-point correlation function. And now here, I don't put a knot. If I were to put a knot, I would have implied that this is in the quadratic theory, but I haven't on the average here. So what this correlation function means is a path integral over fields of my Hamiltonian, which includes h naught minus lambda over 4 factorial integral, and I'm gonna say, okay, fine, my pen is that. I'm gonna use my finger, phi square dot phi square, for instance. Just want to avoid using integrals with my fingers because I have the fingers of a monkey. So I would make a big mess. And then I divide by d phi, and again, the same thing. H naught minus lambda to over 4 factorial phi square dot phi square. And this is a big dot, meaning an integral involved. And of course, this is 1 unless I put phi of x, phi of y in the numerator. This is nothing but a Boltzmann average. Okay. So the idea now is to exploit the assumptions of weak coupling. But as you see, the assumptions of weak coupling is now that the contribution of this term in the exponent and this term in the exponent will affect weakly the correlation function. Right? Or more precisely, what we are going to assume is the following thing: d3x lambda over 4 factorial phi to the 4th of x much smaller than 1. Now, this is the physical assumption. Now, clearly, this can only be done if the system is paramagnetic. Who tells me why? What happens if the system is ferromagnetic? Come on, this is an easy question. What happens if the system is ferromagnetic? Okay, let's go back. If you're ferromagnetic, the values of phi, what is the mean value of phi in your ensemble? Guys, you've done Landau theory, you told me. Have you?
Yeah.
So what happens in the
It's zero.
paramagnetic phase above the ferromagnetic phase transitions? The fields are, on average,
Zero.
0. That means that they oscillate. They will have fluctuation, but it's around 0, right? What happens in the ferromagnetic field, by definition? The fields will not be around 0. So what happens if you integrate and compute the Hamiltonian in the ferromagnetic field? If you have a macroscopic chunk of matter, you will have to you will integrate something that will scale with the volume, right? Because you integrated the finite quantity, and provided you take a larger enough chunk of matter, this will be of order 1. Bye-bye perturbation theory. There's no way you can use perturbation theory to study the non-perturbative regime. Landau theory is a deeply non-perturbative theory. That's why you do other things than perturbation theory. Okay. So here we are doing this, and we say, okay, we are in the ferromagnetic phase. If this is a magnet, but in general, what we are saying is this. Okay, we're assuming we don't have spontaneous chemistry to break it. Okay. Already. So if we can, on the other hand, make this assumption, then we do the only thing we can do other than Gaussian integration in theoretical physics, which is Taylor expansion. So let's expand the numerator and denominator in Taylor series, and we will get h naught 1 minus lambda 4 factorial integral over, I'm going to use the symbol z because later I'm going to have x and y, and I don't want to mess up. Okay. Very good. Now we're gonna use the fact that this is perturbation theory and have something like 1 minus something in the denominator. So you can collect, if you want, this into 2 functional integral, right? So let me write it this way. The numerator will be, I can write this, I can pull out from here a factor z naught, right? So let's look at the denominator for a moment. The denominator can be written in the following way: z naught times 1 minus lambda to 4 factorial integral d3z, and then the expectation value of phi to the fourth in the free theory, right? Because I've pulled out z naught and divided by z naught. So all in all, the denominator is a denominator. So let me look at what happens to the 1 over d. 1 over d is going to be 1 over z naught, 1 minus lambda over 4 factorial integral d4 to the 4, say. And remember, since we are only interested in small effects, now we know that this is a small correction, so we can use the fact that 1 over 1 minus x is roughly 1 plus x plus orders of lambda squared or x squared, right? But we are interested in the lowest order contribution for now. So we can say that 1 over d is to the leading order in our expansion, which is what we are after today, 1 plus lambda 4 factorial integral phi to the fourth. And this is a function of z. And this is an integral in dz. Now, if you go back and look at the numerator instead, the numerator looks like expectation thermal averages in the free theory, quadratic theory, with the only difference that we lack the denominator of the partition function, right, of the free theory. But that's precisely what this overall factor is giving me, right? Sorry, it's again, it froze again. I have no idea why it's frozen again. It says that I'm sharing the screen, but somehow there's a problem with internet being unstable. Now it's back. And I share again. Shoot. I have a problem. Let's give it one more try. Okay, it's back on shape. Let's see. No, doesn't look like it wants to be sharing the screen. It says that I'm sharing the screen, but I'm obviously not sharing the screen. So, okay. So apparently I have to finish this calculation in a very ugly way, but that's the only way we can before. Yeah. So let's see. No. So let's share the screen. And as I will share the screen, I will look at the notes. I apologize for having to use the notes to deliver lectures, but I cannot do otherwise. So these are the notes. Scan through, go to perturbation theory. Okay. Now, the point that I wanted to make is that because you could make the because you were able to expand the partition function of the unperturbed theory below and bring it upstairs, basically all you have is a series of all you have is a series of correlation functions. So now this is the denominator, this is the numerator, and when you combine things, okay, here it comes. So now in the numerator, after you divide out for the denominator, which I put up front here, you see? Can you see my cursor?
No, Professor.
Huh? Sorry?
No, we cannot see the screen.
Ah, I apologize. So I was talking to nobody. Sorry, sorry to you, but so this is the example, right? Can you see it now?
Yes.
So this is the numerator. This is the denominator. In the denominator, say to lead in order, forget about the second term. We didn't touch that. I pulled out a factor Z0. And that's what we just been doing, right? Now let's pull out a factor Z0 in the numerator. Well, if you do that, you get this term, which comes from this, right? Right, I have this, I divide and multiply by Z0, this becomes a thermal average of phi x, phi y in the knot theory. And this term, if you divide by the partition function, multiply by the partition function, you get a partition function outside, and then correlation function in the partition theory, in the free theory of this combination, phi 4, phi 5. Okay? In the denominator, I get a similar combination. And then again, now I'm using, okay, so remember, what is the point now? The point is that all I've done now is reducing the calculation of a two-point function in an interacting theory to a number of calculations in a free theory of arbitrary correlation functions in a free theory, in particular of order 2 and 4, actually 6. Now, you can do any of these calculations by doing big contractions and replacing contractions with propagators, right? So now, even before you do the trick of putting Z2 and putting this term in Z2 in the numerator, let me still keep it in the denominator. I can represent this as a bunch of diagrams and this as a bunch of diagrams, right? So what will they be? Well, let's look at this. There will be diagrams in which I contract X to Z, Z with Z, and Z to Y. Okay? From here. X to one of the Z, Y to one of the Z, and then I'm left with 2Z, Z with Z. And I get something like this. And I have a number of them. How many? Depend on the combinatorics, because the first X have 4 choices. Then the Y has 3 choices. And then the rest is taken. So it's 4 times 3. It's almost factorial. There's a missing 2. Okay? You understand now why there's a factorial term here. And of course, these two have only one interactions, but then of course I have terms with more than than one interactions. Let me forget about them at the moment. I'm only interested in the leading order here, okay? Now, what about the denominator? It has 1, which is Z0 divided by Z0 if you want. And then I have the big contraction of this term here, which is phi with itself times phi with itself. So if I draw it, I get phi with itself times phi with itself integrated over Z. Now you see something interesting is happening here. In the numerator, I get both topologically connected and topologically disconnected diagrams. What am I talking about? This is topologically connected, obviously. This is clearly topologically disconnected. This is topologically connected. This is topologically connected. Don't mess up the concept of connected with reducible, if you have in mind that. I've never spoken about reducible diagram in this course, okay? In the denominator, I've only these connected diagrams. Now, when I pull this forward, I will multiply, but what this diagram really means is an integral over delta delta, right? Now, this integral will multiply the rest here because I'm bringing up to the numerator, right? So there will be a term in which 1 multiplies all of them, and in particular, we get this and this. And I forget about this. These are higher order. I don't care. Okay? And there will be terms like this, which will give me terms like this, you see. And this is a multiplication of 1 delta times an integral of a delta over delta. There's a loop missing here. I'm sorry. There's 2 loops here. Apologize for forgetting a loop here. Well, this is true if circle is a circle, whatever it is. But in general, it really, if I was to relate to this, this is a 2 loop. Okay? Now, what happens is that in the numerator, I have a terms which multiplies a delta times a loop. But when I pull out the numerator, I get another one that does exactly the same, where this loop multiplies this propagator. You see this? But this comes with an opposite sign because of the Taylor property 1 over 1 plus x equal 1 minus x, up to corrections that are higher order. So order by order in perturbation theory, the term in the denominator goes and cancels out exactly the disconnected terms in the numerator. And this happens order by order in perturbation. That means up to corrections that are higher order in the coupling. So the final result to find a perturbation theory can only be obtained by looking at the connected contribution. And the connected contribution looks like this. Once you take into account how many of them you have, you're left with 2 factors downstairs, remember? Now, the idea is that lambda divided by 2 is still much smaller than 1 if lambda is much smaller than 1. Now, unfortunately, if you look at this, it looks fine. If you try to compute it, it diverges because the last delta naught, first of all, the last delta naught will be nasty, right? Because it's really 1 over infinite by itself. Okay? But even the other two are nasty because when z approaches either x or y, I get logarithmic divergences in 3D at least. But that's a dimension-dependent problem. And in fact, you will learn about dimensional regularization if you haven't already. But at least in 3D, that gives rise to divergences. So yes, we were able to solve the problem, but we are facing a problem, infinite divergences. But fortunately, we were prepared for that, because we had this exercise at the beginning of the course in which I was showing you a very, very similar problem. First order perturbation theory, local coupling, infinite contribution to perturbation theory, right? Now we have a local coupling because I can think about phi squared in x and phi squared in y delta x minus y, giving rise to phi to the fourth. That's really local coupling. And I get a divergence. Now it comes at 3 level, not sorry, it comes at 3 leading order perturbation theory, not at next to leading order contribution, as in scattering problems in QED. But never mind, you get these divergences. And we know the physical origin of this divergence. Because why on earth are we allowed to let x go as close as they want to z, or these two z's be close as they want? This is an infinite momentum, infinite resolution statement. I'm assuming I'm controlling predictions for arbitrarily close intervals, which I'm assuming that my theory is valid to arbitrarily short scales. And that's precisely where the theory is supposed to break down. So what do we do? Well, we know the answer. We need to regularize the theory and possibly renormalize the theory. So I'd like to show you how to regularize the theory. Unfortunately, it will be very hard without a pen. I'll do my best in case we pick it up next time. But I want to provide you with a general recipe, and then we go on next time. The idea that everywhere I see a propagator, I can always write its Fourier representation. Right? Now, this is a way of showing, oh, sorry, of course, there's x minus y here. And in particular, the most pathological term that enters in the expression before the ZZ term is the same with nothing here. Right? Now, what happens if you have a collection? Now I'm going to sketch now the idea, because I cannot do much better than that. I have an integral over dz, and then I have these two integrals over dp, dp prime, dp double prime, because I have 3 propagators, remember? Then I have one of them will come with p, and that's going to be z. One of them will come with p prime, and this is going to be z y. And one of them is going to have nothing up here. So let's say 1. And it's going to have p double prime. Let's see if it compiles that. Yeah, not very clear. And yeah, I was able to do that in LaTeX in real time. Fine. Okay? So what I've done, I've taken this diagram and substitute each of them with its own Fourier transform, right? Representation. It's the anti-Fourier transform of his own Fourier transform. It's a bit self-referential, but hey, that's what we do. And why do we want to do that? Because now all the integral in dz only involve the phases, right? And so they will result in a delta function. So the integral in dz will produce one delta function that will eliminate one of these p integral. And what is this? Is going to be p prime. So I'm going to get like two phases. So I'm going to rewrite these phases from here because I don't want to mess up. I'm just rewriting here, right? Of course, I don't have the square anymore. Okay. And then next, I'm gonna collect everywhere I can the z. So let me take one more phase. And in the z, I will get p prime minus p double prime, and I taken out from here. So p prime and p, not p prime and double prime, p prime and p. And I'm taking out from here. Now I'm gonna do the integral over dz of these phases. And what is that? 2 pi to the 3 delta function of p prime minus p, right? Do you see this? So basically the next integral, the one in dz, will give me, go away. I also take away p because I have a delta function. Everywhere I see p, I must put p prime. So everywhere I see p, I put p prime. Every say I say p, I put p prime. This goes away. And if I've done things correctly, which may not be the case, I mean, no, of course, there's not such a thing. I have to put this first factor is not correct. There's this term here. I can put it here. Now I've reduced the problem to still divergent integral because, hey, it was divergent before. Divergent must be still there, right? Sorry, did he stop recording? Tell me he didn't stop recording. No, he didn't. Okay. So, but now I can actually say, okay, these two are redundant. I can do actually this. I might have done some mistake in a calculation. I was doing this in a very inconvenient situation, but let's suppose I did not, okay? But the essence of it won't change. Now, both these integrals are divergent now, logarithmically. So what do I do? Hey, this is an integral of an infinite momentum. Can I have infinite momentum in my theory? No. So I must find a way to regularize this. I can put a Gaussian cutoff, for instance, or anything I like. So I will denote any cutoff here. So I will send this formula to a similar formula in which all of my integrals are performed up to some maximum of scale. Now I can put a Gaussian factor inside the integrals. That's convenient. That's called the smooth cutoff. I can put a step function. That's called a hard cutoff. Result will change for scales near the cutoff, but won't change for infrared physics, okay? And now, of course, the prediction of my theory will be critically dependent on where I put the scale, right? And now I'm gonna do the usual assumption. I'm gonna take the scale to be in somewhere in the middle of a cutoff, of a gap, sorry. And then I'm gonna perform a calculation, match to the experiment, and find a way to replace and basically fit the coefficient lambda, which now, by the principle of maximum confusion, is a function of lambda, where the lambda is the coupling and the second lambda is the cutoff. Of course, I was very unfortunate in using lambda as a cutoff. So let me say capital lambda and capital lambda as a cutoff. Okay? So now I will use this prediction, match to experiment, and find that there is agreement only if my lambda takes a particular value. Now, it turns out that if I change this value, I get a different prediction that doesn't match experiment. So I might conclude that my theory is correct for that value of lambda, right? Now, when you do field theory, you do more complicated stuff that is called, in the renormalization, you introduce counter terms and you do factorizations and you do all sorts of calculations using a Feynman tricks and what's not. And this I leave for the field theory course. I'm after the essence here of it in terms of physics, okay? And the essence is, no matter what you do, you will need to fit a parameter because your theory depends on parameter. And the value you will fit will depend on the trust you have on your theory on the resolution. And if you slightly change the scale, you will get a slightly different result. Therefore, your coupling will depend on the value of lambda you've chosen. And we'll run with the coupling. In this particular formulation that I've given you, I forgot about introducing high local terms to parameterize the physics above the cutoff, right? Remember? And if you do that, then you get all these nice logarithmic running coupling constants, which I will not do here for sake of interest of time and for not repeating things you will see over and over in field theory, hopefully. Okay? But the essence about it is that eventually you will get something that will match to experiments that will depend weakly on the parameter. And therefore you can make contact with experiments after you've fitted one parameter. Okay? Okay, so lecture of today has taught us many things. First of all, how to develop perturbation theory, why disconnected graphs are not there in perturbation theory. But if you play enough with it, say you compute another correlation function, you discover that you will be doing over and over the same things, right? And this is the essence of Feynman rules. Rather than doing this calculation over and over, Feynman rules are a set of graphical rules that tell you how to do this graphically. The other thing that we have seen is that anytime you have a loop, when you go to momentum space, you have unspecified integral, one for every loop. And this comes essentially by Fourier transforming back and forth the propagators. And the third thing is that there's a systematic way of dealing with these infrared ultraviolet divergences, and that's the way field theory likes to do that. Finally, we discover, we already mentioned the cancellation and perturbation theory. Now, I want you to reason about how you work out. So if you look at the notes, you will find the Feynman rules at some point. But one thing you will always notice is how to extract the structure of the vertices from your Hamiltonian. Because you see, if you have a 5 to the 4th, then your vertices will have 4 legs, right? Because you drop 5 to the 4th, and you will have 4 different contractions to the vertex. If you have 5 to the 6th, you will have 6 legs, because you will drop 5 to the 6th, which will lead to 6 different contractions joining the point Z. So basically, after you have done this a couple of times, it becomes immediate to recognize the structure of Feynman rules vertices by looking at the Hamiltonian. Okay, now a typical question that I ask in exam, which I'm not going to go through. So the way my exams usually go is the following. The first question is always completely standard. I take one of the topics, and then I ask the student to tell me about it. And depending on this first question goes, I sort of get an idea whether the student has a deep understanding or a moderate understanding or a weak understanding, which is rarely happening. But in the case I see the student is going very, it seems to be have understood this material. In the second question, normally I try to give him a question that is not exactly one of the topics of the course, but it's a question you can answer given the material of the course. Okay? And because that is for those who want to go, say, to 30, typically. Or maybe they have made a mistake in the first part, but I suspect that they can improve in the second question. Maybe they forgot a term. Fine, everybody forgets. But he seems to be on spot of the material. Let's give him a harder question. Let's see if he finds or she finds his way through it so that he can amend for his mistake. Okay? So for instance, a typical question would be, find the Feynman rules. This is not so difficult, but compute the correlation function, the 2-point correlation function in a theory when you have two fields, let's call it phi and psi, and you have maybe a coupling in the form, I don't know, int I don't know, and compute the correlation function for phi and for psi. I don't know. And then you basically have to recover Feynman rules by looking at the vertices. Now, we didn't cover that of two different fields, but if you have understood what we've done, maybe not today because you're just being exposed to this, but after studying it, you should be able to say, oh, fine, easy, piece of cake, and go ahead. Now, that's a typical question for 30. Now, sometimes people go through this question very easily, and I aim for 30 cum laude. The typical question of 30 cum laude would be, what about this? Sorry, there was a Y here, okay? I got a mistake. Now, this is a case we haven't done at all. And it's not completely trivial how you go from what we have done or what you don't have done. You need intuition. Hey, but that's the low there. It means that you have completely understood the material to a point that you can use it to tackle problems that are not incrementally, but slightly more than incrementally far from what we have done in the course. Okay? So this is all to say, I have had many students that come to me. They seem to have understood because they blah, 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 blah. And then you ask a question such as, not this one, but the previous one. And they cannot find their way through. To me, that means that they haven't understood the course to a point that they want to go for 30. It means that they can be 27, 28, depending on how far they go from this. How much help do they need? 29 if they miss it by a little bit. Okay? So get down to things, not just worry yourself for repeating the demonstration. I don't give a damn of the demonstration if you cannot use the material I teach you. Okay? Likewise, I was pissed off. I'm never really pissed off for didactics, but I was disappointed by the fact that people were super good in demonstrating perturbation theory. And then to the question that I made before, the one that I stopped asking the question, they were failing. Have you understood perturbation theory if you see that the first perturbative correction is actually as large as the unperturbed correction? Probably not. You have understood the math of perturbation theory, but this is physics, not math. Okay? I don't mean to scare you. I mean to put in the right mind frame before the exam, okay? Okay, guys, I'm dead. I haven't slept tonight. I cannot teach with my pen. Next argument will be full of calculations. I'll stop here. See you Thursday.
See you.
Bye.
Bye.